forward. Okay, so here's a list of strong acids that I want you to know for this class. So remember these, commit these to memory, add them onto your flashcards, all right? So we've got hydrochloric, we've got chloric, perchloric, nitric, and sulfuric. These are the common strong acids that you will see in a laboratory, all right? And notice how I did all of these reactions. I kind of showed the reaction in that shorthand way where I put the water over the reaction arrow, and they all generate H+, which, remember, is really like saying H3O+. Technically is more correct, but it's okay to write H+. And now look what is also the other product of these reactions. It's always the anion of the reaction, right? So here is the chloride. Here is the chlorate. Here is the perchlorate, the nitrate. And this one, we haven't encountered this yet, but this is called bisulfate. So if I wrote SO4 2-, right? Let's see where I can do that. I'm going to do that over here. So SO4 2- is sulfate. But when we do these acid-base reactions, we actually just do it with one proton at a time. So you notice sulfuric acid is H2SO4. This means it is diprotic. Don't you love how we make up words in chemistry? So diprotic. So it has two acidic protons. As it turns out, only the first one is strong. So this ion right here, HSO4-, it's not 2- because it still has the one hydrogen attached, which is positively charged. That makes bisulfate. Okay? And so now what this, so really quick, I'll just show you the generic reaction, right? This is the generic reaction for all of these. And notice it's HA. That A stands for anion. Okay, so we can represent any acid reaction as the following. HA plus H2O makes H3O plus. I'll put in parentheses H plus, right? And A-, the anion. Okay, and so now here are the structures of all these acids that I showed you. And what I want to point out, it's always that hydrogen, right? This is showing you the bond that has to break. So this bond, these are all covalent bonds. Okay? And they actually then dissociate to give us these two ionic species, these two ions. So it's pretty cool stuff, right? Because think about it. If you look at all these structures, these are all non-metals. So technically, in the absence of water, these acids are all covalent. But as soon as we put them into water, they readily ionize. They dissolve and they ionize. All right? And so this is showing you all of those bonds that have to break. Like, for example, we know that nitrate is NO3-. Well, here's nitric acid. Okay, so here is the NO3- chunk, right? 1 nitrogen, 3 oxygens. And then there is that H+. Okay? Or like for a more complicated one like sulfuric acid, okay? This whole thing that I'll circle, that is the sulfate. That's the SO4 2-. And you can see to balance that 2-, there is actually these hydrogens that are bonded there. Okay? Same with the perchloric acid, right? Here is the perchlorate, right? The ClO4-. And there's that hydrogen bonded to it. Okay? So let's see, moving forward. So let's talk about bases now. So a base, a good definition is a soluble ionic compound that contains hydroxide. Okay. So keep that in mind, right? I just told you all those strong acids that technically in the absence of water, they are covalent. Okay. The strong bases, however, are ionic compounds. Because look, sodium is a metal. Potassium is a metal. Okay? So it's a metal bonded with a nonmetal. So that means it has to be ionic. And so now if you look at these examples, sodium hydroxide or potassium hydroxide, they dissociate to give you hydroxide. This ion right here, I didn't introduce that in the other slide, but these ions right here are what we call spectators. Okay, so actually I'll back up right here, right? All of these ions right here, these would also be our spectator ions. Spectator ions. So that means they're not really doing much. Okay, they're not really doing much chemistry. It's the H plus that's doing the chemistry in the case of acids, and it's the OH minus that's doing chemistry in the case of bases. So what are some other examples? Well, look, I'm going to pick up my book here. I should have had a table right in front of me. But look, so I'm going to highlight this very first row: sodium, potassium, lithium, et cetera, et cetera, et cetera. Lithium, sodium, potassium, rubidium, cesium, francium, magnesium, calcium, strontium, barium. All of those are good spectator ions to make a strong base with. All right, so let's go through those examples. So lithium hydroxide, okay? Rubidium hydroxide. What about calcium hydroxide? Well, calcium hydroxide definitely, but I have to write it like this because calcium is 2+. Or magnesium hydroxide. That's another good strong base. But remember, because magnesium is 2+, I have to write it like that as well. Okay? So let me follow through my notes. So another thing that we say for basic, so it has these compounds are bases, they have basic properties, would be alkaline. And this has become a funny joke in the running years because I call students out for being basic. Ha 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 ha. Don't be basic, y'all. Be acidic or be alkaline. It's always way much more funnier in the lecture hall. So I'm going to call you out for being basic, and you have to guess what I mean. Are you being a basic, right? Or are you just being alkaline? Okay, moving forward.